Hello, everyone. Thank you for joining our webinar this afternoon. My name is Mariana Sanchez from the marketing department at ECON Tech. Today, we will talk about superheat prediction with artificial intelligence for energy saving. But first, I would like to give a short overview of us. ECON Tech is people, passion, and performance. We develop technological solutions applied to industries in four main divisions: Smart Metrix, which are our data analytics and artificial intelligence solutions; Smart Factory 4.0, which are all our digital transformation solutions; Advanced Robotics, which are applications for cobots; and Industrial Automation, which are PLC programming, technology updates, HMI development, SCADA, and much more. Some of our engineers have more than 25 years of experience in the steel industry. We have 2 offices in Mexico and 1 in Colombia. We have been speakers in international forums like the ICE-Tech and the Digital Transformation Forum. We are Ignition certified integrators and also in Universal Robots. ECON Tech believes in the importance of research. That is why we started our Applied Research Center in 2019. Our speaker is an active member of our research center. Maria Luisa Argaez is mathematical engineer and data science at ECON Tech. She's also a private advisor in data analytics and data science, and a machine learning and deep learning enthusiast. We may have the participation of other members of our Applied Research Center during the Q&A session. Please feel free to share your questions in the chat at any time, and they will be answered at the end of the presentation. Well, the microphone is all yours, Maria. Thank you.
Thank you, Mariana. Well, good afternoon, everybody. My name is Maria Luisa Argaez. I am data scientist at the Applied Research Center of ECON Tech. And today, I'm going to talk to you about one of the many applications of data analytics in the steelworks, which is AI for energy savings superheat prediction. So let's see today's agenda. First, we are going to start with the introduction, the problem statement, and the goal. Subsequently, I'm going to talk about artificial intelligence, machine learning, data science, and the application of it in the auto-heat model. And finally, I will share the results and the conclusions. So, it is fundamental to achieve the best molten steel quality in the secondary metallurgy in the steelworks. The secondary metallurgy involves the ladle furnace, the vacuum degassing, and the continuous casting machine or the ingot casting. As we know, before the last process, the steel was deposited in the tonnage, which distributes the steel in the CCM, in the case of continuous casting. And it is crucial for the steel to arrive at the tonnage with proper temperature, to have a proper casting temperature at an acceptable CCM speed. Well, but how do we compensate for temperature losses since the steel is out from the ladle furnace? Well, we compensate for temperature losses by giving a superheat to the molten steel in the ladle furnace to guarantee an optimum steel temperature to the final casting process. It is well known that the superheat in the steel is the difference between the steel temperature and in the tonnage and in the liquidous temperature. Therefore, ensuring compliance with bad superheat in the tonnage zone within the range of 15 to 30 Celsius degrees is one of the key objectives to maintain a high quality of the final product. Now let's discuss about the project problem statement. Well, the main problem is that the superheat value is unknown and it is given typically by the operator's experience. So temperature samples are taken during the whole process, specifically in the tonnage, to adjust the CCM speed. Nevertheless, sometimes those measurements are not made in a timely manner. Therefore, not knowing the appropriate superheat value to give to the molten steel causes still low or high superheat. So the CCM speed is manipulated to compensate for the superheat variation. And this produces issues regarding quality compliance and operative problems. For instance, when we have a high superheat, means that the steel temperature is higher than the optimum, and it can be compensated by decreasing the CCM speed, but produces very thin solidified layer and breakage in the mold in the solidified product. On the contrary, when we have a low superheat, means that the steel temperature is below the optimum for the casting process, and it can be compensated by incrementing the CCM speed. But this can cause non-metallic inclusions. And non-metallic inclusion can compromise the ductility of the solidified product and thus its mechanical properties. Now let's talk about the energy consumption in the steelworks. Well, due to elevated temperature in the steelworks, it can have high energy consumption, specifically in the electrical furnace and in the ladle furnace. For those reasons, it is necessary to know in advance the feature that affect the superheat and the superheat that must be given to the steel in the ladle furnace to arrive at the tonnage with proper temperature. And this can be achieved with data analytics, machine learning, digitalization, and domain knowledge. So now let's see the objective of this project. Well, here, the main goal is the creation of an artificial intelligence solution to predict the optimal superheat value to give to the molten steel in the ladle furnace to arrive at the tonnage with proper temperature. And this solution allows us to achieve a series of benefits. For example, obtain semi-finished product with adequate quality, avoiding the presence of defects such as cracks and accumulation of pores. Increase furnace productivity by saving time losses that unnecessarily high superheat entails, and making production more efficient by avoiding material discarded due to the presence of defects. Improvement in process control, avoiding variability in the superheat between heat and heat, maintaining optimum CCM speed. And savings in energy consumption in the ladle furnace per heat by avoiding giving an unnecessarily high superheat. All right, now we are going to talk about artificial intelligence, machine learning, and data science. Well, here we can see some concepts that sometimes we use and we don't know what they actually mean. So let's start with artificial intelligence. Well, AI includes computer programs designed to perform certain operations that are considered typical of human intelligence. And machine learning is a subfield of computer science and a branch of AI whose goal is to develop techniques that allow computers to learn. And deep learning is a subfield of machine learning, which is essentially a neural network with 3 or more layers. This neural network attempts to simulate the behavior of human brain, allowing to learn from large amount of data. There are different ways and kind of learning for an algorithm to perform tasks autonomously. One of them is supervised learning. In supervised learning, algorithms work with labeled data, trying to find a function that, given the input condition, can assign the right output label. And the algorithm is trained with historical data and thus learn to assign the right output label to a new value, and that is, it predicts the output value. This learning is often used for classification and regression problems. And here we can see that machine learning have different kind of learnings, and today we are going to focus in the supervised learning. Specifically, this kind of learning has 2 modalities. The first one is the regression, which is in charge of predicting a numerical value. And the second one, the classification approach, is in charge of predicting a categorical value. All right. With the data, typically is divided into at least two parts, which are called training and test data. With the training data, the algorithm is taught to recognize and learn patterns in the data, so it is possible to make the machine learning model. Later, with the test data, it shows how well it learned to recognize one class from another or to estimate a number given the input conditions. Additionally, in regression analysis is a subfield of machine learning whose goal is to establish the method between the features and the output target variable. Here we can mention some machine learning algorithms such as linear regressions, non-linear regression, super vector machines and its variations, nearest neighbors, random forests, artificial neural networks, among others. Now that we know an overview of machine learning, I'm going to talk about the application in the steelworks with the auto-heat model. All right, well, the auto-heat model is made of research where we read and acquire information from several sources, steel domain knowledge where the experience of process engineers and metallurgic experts discusses and help us to build this mathematical construct. Data science tool, which involves several types of statistical analysis and computer science algorithms. And machine learning operations, which is a methodology that helps us to deploy a machine learning algorithm in the industry in a secure and effective way. Well, the auto-heat model aims to predict the superheat value that must be given to the steel in the ladle furnace, allowing to achieve an adequate temperature at the tonnage, to have an optimum time and an optimum CCM speed by obtaining the correct superheat value. And here we consider several process features such as steel grade, heat weight, additives in each process, times, and the transfer times. And this allows us to provide information of the times and temperature at which each heat must be processed. Also, with the benefits of production increase, energy savings, and quality improvement. The auto-heat model also considers process times in the ladle furnace, VD, and at the tonnage. Also considers transfer times from the ladle furnace to the VD and the VD to the tonnage. Here we obtain the optimum casting temperature of the heat by subtracting the temperature losses of the total processes as well as the transfer time to the ladle furnace. Considering the above, now I'm going to talk about the architecture of the mathematical model. All right. Here we can see the auto-heat model. The complete model is divided into two modalities with three submodels. Each submodel is interconnected and dependent on each other. The first section is the forward modality that is in charge of predicting the ladle furnace, vacuum degassing, and the tonnage. For each of them, the final temperature. With the tonnage objective temperature and the CCM speed, with the backward modality, we can obtain the final temperature in the VD and in the LF, and the initial temperature in the ladle furnace. Here, it is important to say that the estimation of each model is an input feature to the consecutive model. Each stage has different features like weight, grade, transfer times, additives, among other factors, and descriptions of operational signals. These features were processed by analyzing them through an exploratory, diagnostic, and inferential data analysis before the predictive data analysis. Because with this kind of analysis, we can see how the feature behavior, detect atypical cases, and select the feature that have the most impact in the response variable. The features were normalized to prevent features of higher magnitude influence more than those features with lower magnitude. For each stage, 7 machine learning models were compared, among which are like random forest, nearest neighbor, artificial neural network, super vector machines. Each model was evaluated with the model performance, which is the mean absolute error, MAE, and the model with the minimum MAE was selected. Also, it is important to say that the same models were also applied, but applying principal component analysis, PCA, to the features and analyzing if the mean absolute error was smaller than the one that the characteristics had without this transformation in order to apply or no the PCA. In conclusion, with this modeling stage, 14 models and their mean absolute error were compared for each of the 6 models that makes the whole superheat model, selecting those models with the lowest mean absolute errors and other model performance factors. Well, now I'm going to talk about the results of the auto-heat model. Well, by selecting the best parameters and the best data science models with the forward model, we obtain the final temperature estimation in the ladle furnace, in the VD, and at the tonnage with a mean absolute error of 5.3, 5.1, and 4.8 Celsius degrees respectively. And with the backward modality, we obtain the final temperature estimation in the VD and in the ladle furnace with a mean absolute error of 4.4 and 1.9 Celsius degrees respectively. And the initial temperature in the ladle furnace with a mean absolute error of 8.7 Celsius degrees. And these temperatures were used to calculate the superheat needed to the heat to reach the proper temperature in the tonnage. So now let's see about the superheat. Well, in this slide, we can see the estimated value in purple color and the actual superheat value in green color. It is seen that the estimation is lower than the real one, since the difference between the actual and the prediction is around 13 Celsius degrees. The temperatures were optimized to save energy, increase productivity, avoiding giving an unnecessarily high superheat. So now let's conclude this webinar. Well, here it is important and essential that nowadays provide new solutions and approaches to share knowledge in the company. The auto-heat model demonstrates good generalization. Therefore, it is suitable for making predictions in the future without supervision. And the mean absolute error was around 5 Celsius degrees in all temperatures. The auto-heat model prediction allows optimized temperature around 13 Celsius degrees. And respecting to the benefits, we can achieve an internal and external quality improvement, productivity increase in the ladle furnace between 7.5 and 8.8%, LF energy savings between 1.5 and 1.8%, and a better process control. It was a pleasure being here today and share these ideas with the steel community and data analytics enthusiasts. We know that artificial intelligence is disrupting our lives and jobs. So let's use it and let's turn our process data into information to achieve better process knowledge.
Well, thank you, Maria, for your presentation. Now we will answer your questions. We have a question here. What about the return of investment?
Okay, the return of investment is usually less than a year, but also it depends on the current plant performance.
Mm-hmm. Okay. Okay, we have another question. Do you have an estimate of time and financial investment of such a project?
All right, well, the time is around 3 to 6 months, but it depends on the steelworks plant. And about the financial investment, it depends on the data acquisition level that the company has. This is fundamental and this is the starting point. That's it.
Okay, good. Are there more questions? I think those are the only questions so far. Let me share with you the email address of Maria, just in case you would like to know a little bit more about this model, or if you have further questions, please feel free to contact her. And well, thank you for joining our webinar, and thank you. Have a very, very good afternoon. Oh, I'm sorry, we have one question here. Did you use the operator settings at the output for training?
For the data training, well, we try to acquire all the data that each steelwork has in order to make a larger data set with the most features and the most samples that we can have. So we also consider conditions to run the auto heat model.